Hi, myself Vinayak and my friend Sahil. We worked on OCR for Hindi language handwritten text. In the project, we implemented and trained the model inspired from state-of-the-art English OCR on Hindi dataset and compared it against the present state-of-the-art model's performance for the same. Next slide. Core objective of the project is to map Hindi handwritten text to the image in the image to machine readable Unicode text. Research for Hindi language is lagging a lot behind high resource languages like English, primarily due to unavailability of the well-anotated dataset for Hindi language and also current state-of-the-art models using the outdated model architectures. Next slide. Hindi is the official language of India and it has roughly 500 million speakers. Even today, handwritten Hindi is used widely in fields like logistics, banking, and health sectors. And a good OCR model like the one we are working on would help digitalize all of this data and better process them. Next slide. Like mentioned previously, a key problem with Hindi handwritten text recognition was the unavailability of the well-anotated dataset. And very recently, such a dataset was published for research purpose. This dataset has total 95,000 images from 12 different writers of varying age and educational background. It is on par with the English language equivalent IM dataset, which is used for benchmarking the performance of different models for the English language. And availability of this new dataset for Hindi language has opened new avenues of research for a Hindi language. Next slide. Current set of the model for this dataset, it uses the pre-trained resonant architecture based model to extract the visual features from the image. These features are then passed to the bidirectional LSTM layers to predict the sequence of Hindi characters in the image. We trained a model with this architecture on the dataset to generate the baseline of the results to compare against the model that we developed. Now Sahil will walk you through rest of the presentation.
The second approach that we tried was using a transformer-based architecture where we train the decoder of a transformer to directly learn correlation between the input image and the output text. During training, the input image is divided into several patches. These patches are converted into patch embeddings using a convolutional layer. To this, we add positional embeddings. Optionally, a visual encoder is also used, which helps us learn the long-range dependencies between patches. We then add separator token and append the text embedding. The concatenated embedding is fed to the decoder, which then learns the associations using masked self-attention. During inferencing, the patch embedding along with positional encoding and visual encoding encoder output is directly fed to the decoder, which gives us the output string. Now, a comparison of the accuracies and word error rate. The CNN plus BILSTM, which is the state of the art for Hindi, has about 27% of word error rate. We realized that using a transformer-based approach, the word error rate reduces to 24.6%, and adding a visual encoder on top of that gives us even better performance, and we achieved a word error rate of 19.95%. Since Hindi language has several nuances which make it different from English language, we observed several challenges. One was tokenizer mismatch, since we had to resize the embedding layer to make sure the Hindi tokenizer output is compatible with it. We also had to do explicit end of sentence handling. We realized that in the initial implementations, the output was appended with the output which had correct string was appended with some garbage text. Explicit end of sentence handling helped us get rid of that. The computational cost was also quite high, and every training, every iteration and improvement over the model took all more than 24 hours for us to test the results, limiting the number of permutations we could try. Future directions, we would like to try a lexicon-based approach on also spatial transformer network to handle skewness and other variations in the Hindi text. In summary and conclusion, we implemented two architectures from reference papers with our improvements. We ported English SOTA to Hindi language, and we realized that English SOTA does help improve errors in the Hindi word error rate. Thank you for your time, and thank you for your attention.